This lecture is part 1 of section 3.6 from Math 311, a course in linear algebra at Western Illinois University. So in this section we're going to be talking about functions, particularly functions that take vectors to other vectors, or in some cases points to other points in Rn. And I want to start off with two examples that we're more or less kind of familiar with. The first one is a rotation of a point, counterclockwise 90 degrees. Okay, we can also think of this as the rotation of two vectors in rotation of a vector in R2. We basically, if you remember, if we take the point xy and you interchange the coordinates and multiply the y by -1, that corresponds to a rotation through 90 degrees. And if you're not quite sure about this, if you just consider this as a vector, this vector xy, and this is a vector -yx, if you take the dot product, you get 0. So those vectors are orthogonal or perpendicular to each other. So this is 90 degrees. Okay, and this, we're going to see that this actually has a very nice property, but you'll notice that this xy, we can decompose it as x times 1, 0 plus y times 0, 1. And then this will be minus y times 1, 0 plus x times 0, 1. And you'll see that that this vector 1, 0, if we apply this rotation, we get 0 minus 0 minus 1, and we'll see that actually maybe I could write it this way. This will be x times 0, 1, and this is plus y times minus 1, 0. And this 1, 0 is actually the rotation of 1, 0. And this minus 1, 0 is the rotation of 0, 1. So actually we basically just wrote this as a linear combination of actually a standard basis, and we apply the rotation to each basis member here, and we get the output. Okay, we're going to see that this is not an accident. Okay, we could also talk about a projection of a point in R3 onto the xy plane. Basically, we're just sending a point here to the point under it or above it in the plane z equals 0. That's what the xy plane is. And once again, we write this as a linear combination of standard basis of R3. So this would be 1, 0, 0 plus z times 0, 0, 1. If we apply this projection to each of these, this is just going to be x times 1, 0, 0 plus y times 0, 1, 0, and z times 0, 0, 0. Okay. Basically, if we apply these 2 points, these two points are already in the xy plane, and this is not, and the projection of that would be here. So, the general formula for this projection would be, well, here it would be t of x, y, z would be just x, y, 0. And here the formula for that, for the rotation, t of xy would be minus yx. And we're going to see that both of these functions have a very nice property. They're in fact linear transformations. And these are functions that preserve the linearity. To be more specific, they preserve the vector addition and scalar multiplication. And even more specifically, what that means is this following. You see in this definition, a linear transformation from Rn to Rm is a function t, which takes inputs from Rn and spits out outputs in Rm, such that both these properties hold. That T of u plus v is T of u plus T of v for any vectors u and v, and T of c times u is equal to c times T of u for any real number c and any vector u. Okay. So again, this preserves, we say this means it preserves vector addition. This means that it preserves scalar multiplication. Now, as a result of this, these definitions, we can actually extend make some conclusions here. If we wanted, if let's say we just wanted to apply t to a linear combination of two vectors, this is because this is a sum. We know that this will be t of this vector plus t of this vector, so we get t of c1 v1 plus t of c2 v2 for any real numbers c1 and c2 and vectors v1 v2. And then because of the second property, we can pull these real numbers, these scalar c's out, and we get c1 t of v1 plus c2 t of v2. And then it's also, we can sort of extend this for any finite linear sum. We see up here that in general, if we take t of c1 v1 plus c2 v2 plus dot 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 plus ck vk, then this is going to be c1 times t of v1 plus c2 t of v2 dot 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 plus ck t of vk. So you can do that as long as t is a linear transformation. Now we're going to see that these two examples are in fact linear transformations, because up here if we apply t of, let's say, x1 y1 plus x2 y2, this is going to be t of x1 plus y1, or at x2 y1 plus y2, and then this will be, the output says that this should be minus y1 plus y2, x1 plus x2, and this is going to be, if we break this up, this is minus y1 x1 plus minus y2 x2, and this is t of x1 y1 plus t of x2 y2. Okay, so this certainly preserves vector addition, and in fact if we compute t of c times x1 y1, this is t of c x1 c y1, which is minus c y1 c x1, which is c times minus y1 x1, which is c of t of x1 y1. Okay, so this preserves scalar multiplication. Okay, so sorry, made this a little messy, but hopefully you can see this. All right. In the second example, I think you can see it's also pretty straightforward that this is a linear transformation. If we take t of x1 y1 z1 plus x2 y2 z2, this will be t of x1 plus x2 y1 plus y2 z1 plus z2, and this is just going to be x1 plus x2 y1 plus y2 0, which is x1 y1 0 plus x2 y2 0, which is t of x1 y1 z1 plus t of x2 y2 z2. Okay, so it preserves vector addition, and then I think you can also see that t of c x1 y1 y1, z1 is, okay, so this is cx1, cy1, cz1, t of that, which is just cx1, cy1, 0, which is c times x1, y1, 0, which was c times t of x1, y1, z1. Sorry, I did not leave myself much space here, but hopefully you can see that this does work. Okay, and you can read my writing and maybe blow things up just to check. Right. So these are two linear transformations, and we're coming back to these two examples again. On the next page, let's check and see. You can also check that, see if these examples are linear transformations. I think you can see here. This is a case where the inputs and outputs are from different sets, but that's okay. It will still be a valid function, and we can see that t of let's say x1, y1, z1 plus x2, y2, z2 is t of the sum and t sends whatever it is. It's going to be 2 times the x coordinate and then the z coordinate. Okay, and then we can break this up. This is 2x1 plus 2x2, and then we can break up the vectors as 2x1 z1 plus 2x2 z2, which is t of x1 y1 z1 plus t of x1 y1 z2, rather 2 should be 2's. Okay. All right, and then the scalar multiplication will be again t of c x1 y1 z1. This is t of cx1 cy1 cz1, which is now going to be 2 cx1 and cz1. You can factor out a c. And that's c times t of x1 y1 z1. Okay. So this is a linear transformation. I'm going to leave it to you to check that this is also a linear transformation. Okay, you can do that. We'll come back to this vector and this way, and we're going to see there's an easier way to check. But let's look at this example C. So this sends the vector xy to x times y times 2y. And this turns out this will not be a linear transformation, and it's because of this xy here. Because we can see that t of xy, let's say x1 y1 plus x2 y2 is going to be t of x1 plus x2 y1 plus y2, and then t sends this to the vector x1 plus x2 times y1 plus y2, 2 times y1 plus y2. Whereas if you compute t of x1 y1 plus t of x2 y2, this is going to be x1 y1 2y1, and this will be x2 y2 2y2. Okay, or just x1, y1 plus x2, y2, 2y1 plus 2y2. Okay. And you can check that these are not equal, because at this coordinate is not equal to this. If you multiply this out, you do not get this. You get a couple more terms. Okay. So this is not equal, and this is not a linear transformation. Okay. You could also just find, pick two arbitrary points. And in general, if something's not linear, it's not going to be too hard to find a specific counterexample. So we can maybe do it in this case, in this next case. T of R3. T goes from R3 to R3 and sends the vector x, y, z to x plus y, x minus y, z plus 1. And, well, let's just do that. Let's take the vectors 0, 0, 1 and 0, 0, 2, maybe. It's going to be T of 0, 0, 3. And the result will be, well, x plus y is 0, x minus y is 0, and this is 3 plus 1 is 4. But you can check that T of 0, 0, 0, 0, 0, 1 and T of 0, 0, 2 is going to be 0, 0, 2, so that's 1 plus 1, and T of 0, 0, 2 will be 0, 0, 2 plus 1 is 3, which is 0, 0, 5, and these are not equal. Okay, so this is also going to be a linear transform. This will not be a linear transformation either. Okay, all you need to do is here you go. All you need to do is find one of those two properties that doesn't work. Part E. Here is a vector here's a function that just takes a vector in R2 and multiplies by 6. I think you can do it directly component-wise, or you can just notice that this vector is actually T of V times 6V, right? That's essentially what this function is defined, and you can clearly see that T of V1 plus V2 will be 6V1 plus V2, which is 6V1 plus 6V2, which is T of V1 plus T of V2. And we also get that little c times T of V1 will be c times 6V1, which of course will be 6 times CV1, which is T of CV1. Okay, guess I did it in the other direction, but that's fine too. Okay. Okay, so this is a linear transformation. And in fact, there's nothing special about the number 6 here. You can multiply multiply a vector by any constant, and this will always be a linear transformation. Okay, now another linear transformation can just be multiplying a vector by a matrix if it's the right dimensions. So we come to our first fact of this lecture. If A is any n by n matrix, then the function t, that is defined by this equation T of v equals AV, is a linear transformation from Rn to Rm. Okay, notice that if A is an m by n matrix and V is a column vector, it's n by 1. So the result is going to be have m rows and 1 column. Okay, so it'll be an Rm. And this is not very hard to show why this is true. It's basically properties of matrices that we already know. Why is this true? Well, T of V1 plus V2 is going to be A times V1 plus V2 by definition, and then by the distributive law for matrices, we get AV1 plus AV2, and this is T of V1 plus T of V2. And then we have the T of CV1 is going to be A times CV1. By the associativity property, this is C times AV1, which is C times T of V1. Okay, so this is a linear transformation. So this is not that shocking. What is a little more shocking is that every linear transformation from Rn to Rm is of this form. That is, for any linear transformation, no matter how it's defined, we can find a matrix for which this is true. And that's the fact. That's fact 2. Okay, if T is a linear transformation, then T of V is equal to A type B for some m by n matrix A. All right, so why is this true? All right, so well, we have that remember, every Rn has a standard basis, right? We can say that remember that if E1 is vector 1 followed by zeros, right? E2 is 0, 1, 0, dot, dot, and then En would be 0, 0, 0, 1. Okay, so again, this is remember, this is the standard basis for Rn. So if V is in Rn, you know, and let's say V is, I don't know, let's say x1, x2, xn, then this is the same thing as saying x1 E1 plus x2 E2 plus dot 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 plus xn En. Okay, and then T of V, is just going to be T of x1 E1 plus x2 E2 plus dot 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 xn En. And then by the properties of linear transformations, this is x1 T of E1 plus x2 T of E2 plus dot 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 xn T of En. Okay. All right. Now, okay, so that is that. Now, notice that this, as a matrix, we can actually write this as this matrix because where this T of E1, remember, T of E1 is going to be a column vector with m entries, right? So they're actually going to be m. So this is the matrix where the first column is T of E1, the second column is T of E2, and so on, right? And this, we've seen that this linear combination can in fact be expressed as the product of this matrix and this column vector. And of course this vector is just V, of course, right? So this is what we call this AT, and then this is V, right? So this is going to be AT times V. This is called the standard matrix of T. So every linear so t of v can be expressed as at times v for this. If you use this formula for the standard matrix, you just have to take it compute column by column. So if we go back to our examples of the linear transformations that we had, in this example, in example 1, where we had t of xy was minus yx, then this was just this t of e1 was t of 1 0, which was just 0 or minus 0 1, right, which is the same thing as 0 1, and t of e2 was t of 0 1, which was minus 1 0. Okay, so the standard matrix was 0 1 minus 1 0, and sure enough, we take this matrix and we multiply it by xy. Okay, that is equal to this. So that would be the standard matrix. In example 2 that we had here, where t of xyz is equal to xy0, okay, in this case t of e1 is t of 1 0 0, which is 1 0 0. T of e2 is t of 0 0 1 0, which is 0 1 0. And t of e3, which is t of 0 0 1, is 0 0 0. Okay, the z, remember in all these cases, the z coordinate is replaced by 0, right? And so the standard matrix would be 1 0 0, 0 1 0, and 0 0 0. Okay. That would be the standard matrix. And sure enough, you can check that this times xyz is equal to this. So that would be the standard matrix. If we go back to one of the examples we saw before here, B, in this case we had a, if we do the same thing here, we get t of e1 is t of 1 0, which in this case would be 2 times 1 plus 0, and then negative 1 plus 3 times 0, which is 2 negative 1. T of e2 would be t of 0 1, which is 2 times 0 plus 1, and negative 0 plus 3 times 1. So this would be 1 3. So the standard matrix here would be 2 negative 1 1 3. That would be the standard matrix. And sure enough, if you multiply this by xy, you get 2x plus 1y, and then negative x plus 3y, which is actually equal to this. So we can see that t of xy is this. So we can see that right here, t of v is actually a matrix times v, and that's always a linear transformation. So that's in some cases it's pretty easy to see what the matrix would be. You can also check here what the matrix for in example 3, the standard matrix, would be, well, for 1 0 0, that would just be 2 times 1 and then 0. for t of 0, 1, 0, that's when y is 0, y is 1, x and z are both 0, so this would be 0, 0. And then for 0, 0, 1, this would be 2 times 0 and 1. Okay, so that would be the standard matrix here. Okay, and not surprisingly down here, that in this case, the standard matrix would be 6, 0, and 0, 6. Basically 6 times the identity matrix, which is basically what this is. Okay. All right. So every transformation has a matrix representation. Okay. And that's the I think right now that's a good place to stop part 1, and we'll see you next time.